completely sure they're gonna get the amount of CFM just drawn in, because there's not that much air leaving the house. But they claim they've been, I don't think anybody's here. They claim that they've been getting outside air is drawn into that return with nothing's leaving.
Right.
And they're claiming that they're getting it, they're actually put a damper in the throttle it back, because I was really surprised, like, well, there's not that much air leaving if you need 100 CFMs or 150 CFMs, and they're like, no, it's pulling in that much. They're actually putting the damper to throttle it back, and then the controls to open and close it completely.
Right.
So, but yeah, they're supposed to get some installed here, and then I'm gonna see some testing just to sort of satisfy my curiosity. They claim they're getting it. So.
This is a question I have too, so if you don't mind. I'll find another. But so when you're doing this, and you're doing it basically on the 25% intermittent usage, so that's multiplying your requirement by 4. So if we're at 45 CFM, you're now up to 180 CFM in that case. So what are you relying on to pull the air out? You just add exhaust? Okay. So, but that's much more random, or that's the one thing about this method. It's, you don't have a predictable balancing effect if you're relying on bath exhaust in that case.
That's right. That's why I'm here to maybe find a better way.
Okay, all right, great. Good. I'm here to help you. We have a common cause. Okay, so by asking the question, obviously we got ahead of the slides a little bit, but supply-only methods are obviously independent, or you can integrate them with the HVAC, and I think we would agree that makes the most sense. So typically involves duct fan that brings air in the return line of forced air system, circulates the forced air system circulates the air for the home. Now, according to this slide, we're pressurizing all portions of the home and forcing air out. So we have a positive in that house. Pros, more even distribution, minimal addition of ductwork, and you have a known source of where the outside air is coming from. And the cons we've kind of already discussed, except for this, that we're adding unit air into its exhaust walls. But the other thing is what we're doing in that case, and just look at the idea of a 45 CFM requirement, and now we're bringing 100% outside, 180 CFM of untreated outside air, and we're dumping it into a return. And then that puts a load on the mechanical HVAC system. And one of the things that which I hope we'll get to, I'll make a point of getting to, is we have a quick calc program that will show you the impact of the outside air on an existing HVAC system. And I put together a quick sample of that. Ironically, the value there is 180 CFM. So we'll be able to see exactly what that what it adds to the loads. Okay. Balance system option, that's really more what we're here to talk about. So we'll get into that. Can be independently ducted, integrated with the HVAC system, or a standalone unit. How it works, we supply, our system supply, our combined supply and exhaust systems. We say, well, where can you use a balanced device? And that's anywhere where an exhaust airstream comes in near contact with an incoming airstream. Those systems have built-in heat recovery capabilities, so heat is transferred between the exhaust air and the supply air. We'll get into the specifics of that. Some systems are also capable of transferring moisture. So here we get into one of the Renew Air slides. So these are the balanced airflow options. We're going to talk about ERVs, or energy recovery ventilators. There's a whole, a lot of nomenclature that surrounds these different devices. Energy recovery ventilator is the proper one. Heat exchangers, central and lake recovery, energy wheels, static plate cores, and for the most part, they all apply. Heat recovery ventilators are just that. They recover only heat It's sensible only. It is a heat exchanger. These are some of the common media or heat exchange packages that are available. Heat recovery ventilators are pretty much going to come in one flavor, if you will. It's a static plate core that's going to be made of aluminum or plastic. It is sensible only in recovery. In other words, sensible heat, that heat which you can feel, something other than latent. The total effectiveness, I've given away the show. The total effectiveness is going to be limited to about 20 to 30%. There are a lot of manufacturers of the finished devices as well as core materials. Just to present a complete picture here, in the ERV category, or energy recovery ventilator category, there are basically two different options. One is an ERV wheel or an enthalpy wheel that will do a sensible and latent exchange, and those wheels will come in a number of different materials. Aluminum, synthetic fiber, or a polymer would be the typical way these things are transferring both sensible and latent heat. Very good total effectiveness. These are typically seen in commercial applications. I know years ago, Honeywell used to have a small ERV wheel in a residential model. I don't know that you can find wheels in ERVs that are applicable for the residential market. Can anybody in the HVAC world offer an opinion there? Okay. So it was not my intention to spend a lot of time on enthalpy wheels. If you're a commercial builder or contractor here and you want to have a further conversation about that, I'd be happy to do that with you. More typical will be in the ERV category will be an enthalpy core and an enthalpy fixed plate heat exchanger. There aren't a lot of manufacturers that make this type of core. The core that Renewair uses, S&P is a company that actually technically owns Renewair, and there are some, they market some of these cores, but Mitsubishi makes the core. But Renewair, since 1983, has had the license to sell the Mitsubishi cores in the United States. So, does it matter what the differences are? Anybody have an opinion there? And anybody here, particularly on the HVAC side or on the builder side, used either one of these balanced flow property or products? And are you using ERDs or HRDs? Okay. So heat recovery ventilator.
Mainly the job. All.
Okay. And they're requiring you there to do balanced flow?
Most of them have it. They just have to put it in the end.
Yeah. So in other words, you're going against that that axiom that it's easier to ask for forgiveness than permission?
We'd rather be proactive than forget.
Sorry, Jim. Yeah, that's a good idea. It's usually cheaper that way. Okay, just to cover, well, we do feel that there's a big difference between heat recovery ventilators and energy recovery ventilators. So let's look at what a heat recovery ventilator does first. It transfers temperature differential through the core, and that is sensible heat only. It makes use of aluminum or plastic cores. Now, because of the fact that it's transferring sensible heat only, but there's always a latent component in that in the air, that means that you're likely to get condensation on that aluminum or plastic core. The aluminum can freeze, but at the very least, you're going to require a condensate pan and a drain, and that must be considered during the installation process. It cannot be, it has to be installed in a particular way, and it must be level. It's like anything else that's going to have a condensation factor. And you do require a defrost cycle with HRVs. Am I saying anything that you haven't encountered? Okay. So the defrost cycle is where during the winter months, that condensation is going to form in the core, and you're going to have to basically shut the unit down and find it. There are different methods for defrost cycles with HRV. Some of them are as simple as a light bulb within the body, within the unit, and it'll just shut it down and bring on the light as a source of heat. But there is virtually no latent exchange, and it leads to very poor summer performance. And the fact is, some people just turn them off during the summer. We'll contrast that with energy recovery ventilators now. First of all, the most important thing is they transfer both sensible and latent heat or humidity. The two methods, as I touched on, are desiccant heat wheels or enthalpic plate cores. What we'll talk about today are enthalpic plate cores. There are no condensate fans or drains required. There is no defrost cycle. There is no frosting in the core. Entrained water vapor will transfer through the plate from one airstream to the other. We'll show you how that happens. But because of that, these two things are not required. The other fact is that it can be installed in any configuration. I have a couple of slides that will show installations that make use of that fact. It is an effective energy exchange in all seasons. And again, one of the things I'll show you at the very end of this is what we call ERV calc. And we take a specific example and we'll show you what the effectiveness is. And I would encourage you to just take a look at that, the link that I'll share with you. So HRV cores, kind of covered most of this already. I tend to get ahead of my own slides. But there are numerous manufacturers of this. It's always going to be aluminum or a type of plastic. And we talked about the performance issues. This is the one slide I have on enthalpy wheels. Again, this really is a commercial product, but just so you are fully informed, this just gives you an idea of what happens on a desiccant heat wheel or an enthalpy wheel. You've got exhaust air crossing through the wheel material. By the way, that wheel is rotating constantly. And you've got exhaust air moving through the wheel on one side. As it turns into, it will absorb heat and moisture and will turn into the other airstream, and it gives up that heat and moisture. The issues with enthalpy wheels is, well, first of all, because of the nature of the desiccant, does a very good latent exchange, as well as the sensible exchange. It will outperform a static plate enthalpy core on the latent exchange. But you're giving up a lot for that. You've got a lot of moving parts here, and the maintenance on it is much higher. You also run the risk of building up frost in that core. So that's the quick version of enthalpy wheels. Now, enthalpy cores, on the other hand, are completely different. What we're doing here is very similar to the same thing that an HRV does, with a significant twist. So what we're doing is exhausting room air through an air passage, separating that air passage from a perpendicular or an opposed air passage is this thin plate. So when we say static plate, fixed plate, heat exchanger, this is the plate we're referring to. So you've got two opposed air passages. And what's happening there is that both sensible and latent heat will transfer through that plate. The beauty of this thing is, and I have to tell you that just by way of a little history, I was in a booth at the ASHRAE show one time, and one time I saw these cores there. The large units have cores that are 23-inch cubes that are a basic building block. And I saw this core sitting there, and I'm looking at this, and they're telling me what it did, and I said, how's that do that? It just made no sense to me. But I was captivated from the very beginning there. So the beauty of this is that heat will always transfer to cold, right? And a heavier concentration of water vapor will transfer to a drier air, from a wet air stream to a dry air stream. It's a natural transfer. So what that means is, when you think about it, in the summer, where we're exhausting cold, dry air that we've paid to condition, right? We have paid to make this air cold and dry. We're exhausting that air through this airway, and we're bringing in warm, moist air, right? Which we're now going to have to, again, pay to condition. Except what we're doing is naturally transferring heat from one airstream to the colder airstream, and the more saturated airstream will give up vapor to the drier airstream. And there are no moving parts. It's that's what just amazed me from the very beginning. So the transfer performance, air passages are perpendicular. We're going to pass through each airstream through the plate material. Sensible exchanges via conduction, latent exchanges via diffusion. I have a slide that may explain that a little bit better. The thing about the airflow through these cores is that it is a laminar airflow. Why is that important? The laminar airflow creates a turbulence through the core so that anything that escapes the filters, and generally that's going to be small particulates, will be carried through the flutes or the passageways in the core. The laminar flow allows us to say that these cores will not block or clog. Typical velocity, it falls in this range, and the static pressure loss typically really is more like a ½ inch through the core. So a more simple way to say it, the static plate core allows exhaust outside air streams to cross paths in the core, transferring both heat and moisture in the process. Everybody good with that? Any questions? Okay. We'll get into the how it does this. You know, one of the things that's important about any balanced system, keep in mind now, we are exhausting what would be, we'll call it air in the house that may carry contaminants or smells that we don't want, particularly bath exhaust. We'll tell you that you can use the ERDs in place of bath exhaust. So what are we doing there? We're actually taking bath exhaust and passing it through this core. One of the